Hey everybody, today we're going to be doing a little tutorial on getting started with R. By now you should have R and RStudio downloaded and installed on your machine. So I'm going to do a brief overview of all the windows and walk through this brief exercise together. So once you have it installed, you may notice that RStudio, again, once you install R, you'll never have to open it again. If you've also installed RStudio. So RStudio is the graphical user interface that wraps around the traditional base R program. So once you have RStudio installed, you never have to open R again. Once you open RStudio, you'll see that you may have three windows here. You'll have this console window, you'll have the environment, and the viewer window without this one. For example, if we open up R, should look like this. Sometimes it looks like that, right? Where we're going to have just three windows. But to add another window, we're going to go here to the add button up here at the top and then open up a new R script. That will open up that script window. So quickly, a brief overview. We have this script window, which is in the upper left-hand corner. That script window is where we're going to type all of our code. So we'll say 3 plus 2, maybe 3 squared. Another way of writing 3 squared is 3 squared, right? You see we hit enter and nothing happened to those, right? And this is because it's a script window. It's like pre-writing a paper before you turn it in. We haven't submitted it to the R console yet, which takes us to the next step, which is the R console, that bottom left-hand window. That bottom left-hand window is where we're going to submit all of our text, all of our code, right? So if I wanted to, I can come down here and just write 3 plus 2, hit enter, and we'll get 5. 3 squared, get 9. Another version is 3 squared and get 9, right? And you'll notice it responds immediately after with the answer, right? If I wanted to clear that window, hit Control L, and we can clear the console, so there's nothing written in there now. Right? The console is where you're going to be running all of your code, right? For example, if I wanted to run all three lines of these code down here, I could either, copy and paste it, so Command C in a Mac or Control C and the PC, and then Command V to paste it into the bottom window, the console window, or Control C on a PC, or Control V on a PC into that bottom window, and then hit enter. It will give me the answers to all of that stuff. Right? I'll clear that window again with Control L. Or I can highlight everything, and instead of copying and pasting into the console, we just hit run. It runs all three of those lines. I'm going to clear that window again with Control L. Another way of doing that is on a Mac, hitting Command plus enter or Command plus return. So we hit everything's highlighted up here, Command return, and it runs all three of those lines. On a PC, instead of command, it's going to be control. So it's going to be control plus return or control plus enter, and it would run those lines. So that's a quick little shortcut of how to run your lines of code without having to click run or highlight and copy it and paste it into the console window. Okay, I'll clear that again. Let's clear this window up here as well. The next window is the upper right-hand corner, and this is the environment window. In the environment window, we're going to have all of our data sets show up. So if we import a data set or pull in a data set, which is, it could be various formats. Oftentimes that's going to be in a spreadsheet format, like a CSV or an Excel format. We can pull that in, tell R, hey, use this data set. This is our own data set from our local machine. Use this data set in the analysis that we're going to be running. It'll pull it in, and then it'll pop up there on the right-hand side in this environment window. And as I previously mentioned, R also runs with essentially data sets in the quote unquote cloud, right? So once packages are developed, they're hosted on a server somewhere, quote unquote, in the cloud, and those packages often come with data sets attached to them. So once these data sets are in that cloud, you can pull and use those data sets. And we'll walk through an example of how to do that in the next couple of steps. So that once we pull that data set into our um, environment here, it'll pop up into this environment window. And right now the environment is empty. And then finally, that last right-hand window is the plot window or the viewer window. And this is where if you run a bar chart or a pie chart or a histogram, um, anything like that, you're doing maps, all of that will show up or appear in this bottom right-hand window. And you can export those as images and save them elsewhere. Also, in this window, you'll see files. So it'll start, um, R will have a list of files from your home directory. It'll list all the packages that you have installed on your computer, including ones with a check mark, which means that they are um, currently running on your computer. So all of these packages have been installed on my computer, but the ones with the check marks are currently pulled into working memory. You have help pages for various R documentation, and then you have a viewer window. So the plots will go there. The viewer will also show various images. All right, so that's the overview of what R looks like. So how do we get familiar with R? Like I said before, R works with packages, and these packages are hosted in the cloud. They don't automatically come with these packages. You have to tell R to bring those packages create a small, condensed local copy on your machine. Now, installing these packages just creates a copy on your machine, a small version of it. To actually work with it, those packages is the next step. So the important thing about R is it tries to keep the um, computing power and the size of R really small. So it separates the program from the packages and the packages from actually using the packages. So it's kind of a three-stage or three-step process. You have to first tell R, get these packages because I need to do this specific thing. Make a local copy. Once you've made a local copy, then you can say, oh, I want to use that right now. Maybe later you don't want to use that package, right? There's a specific kind of method you want to run. You don't want R to open up and load that specific package and that method every time it opens, right? That's because we could have hundreds or thousands of packages, and that's going to take longer and longer for R to load and run those methods, right? It gets clunked down. So to solve for that problem, it says, we'll make those copies on your machine, and then we'll take a next step, and you tell me when you want to use those. I'm not just going to assume that you want to use these packages all the time. So here, you'll notice I have some lines of code to install packages from the repository, the cloud for R. And the code is just install.packages with parentheses and then quotation marks. And then inside the quotation marks, it's the name of the package that you want to install. All right, so I'll highlight this first line, install.packages, mass. So highlight that and paste that there. And you'll notice this install.packages, in between that quotation mark, it became green, saying this is the name of the package. Right? We can even start typing out. So the next package is the psych package. So I'm going to say install, and look, the brilliant R program is able to predict what you're going to type. Is it install.packages or installed.packages? Install.packages, that first one that's highlighted, is what we want. Right? It tells R, go out and look in the cloud, look on these servers in this repository, and download this package for me. Install it on my own machine. Installed packages is simply, it tells you which ones you have installed on your machine. So it runs through the list of the local copies, right? So the one we want is install.packages. So the next one we said was going to be psych, correct? So I can highlight that, copy and paste it into that bottom window, or I could just, in those parentheses, I'll type one quotation mark, and look, again, R is a smart program. So when you type one quotation mark, it says you're going to need another one on the end of it. So it predicted that. So typed out the second quotation mark for me. And I said the next one's called psych, right? That's wrong. It's here that psych is in lowercase. And it's important to remember that because R is case sensitive in this way, right? There might be a package named psych, all caps, and also there's a different package that might be called psych in lowercase. Many times that's not the case. If I tried to install this psych all caps, it'd say something to the effect of there's no package named psych, like this. So it's looking for the specific spelling of that package. So we need to fix that and change it to psych. Right? So these other packages, I'll go ahead here, copy and paste them in. Here we go. And you'll notice that here on this fourth line, I have a little hashtag in front, and that whole line of text is greened out. Now you'll notice in this getting familiar with R web page, I mentioned that when you're working with a script, you'll see something like this in your script where you have a hashtag or a pound sign before some text or a line of code, and it'll green it out, much like we have here. Greening out is called a comment. When you put a hashtag in front of some line of text or some line of code in R or your R script, it just greens it out, it comments it out. It tells R, don't run this as an actual line of code. Run it as just text that represents a note to myself. Right? So we'll do that. So note, we don't see anything down here in our console window, and that's because we haven't run anything. So to actually run it, we highlight it, again, hit Command Return or Control Enter, or select the Run button. So I'll hit Run here, and we'll run, and we'll see that these packages are starting to download. Right, so you'll know it's run correctly when you see the downloaded binary packages are in. The downloaded binary packages are in. The downloaded binary packages are in. So it ran all three of those lines of code. When it got to install.packages rcurl, which was greened out, commented out, we see the comment there, the hashtag there. It didn't do anything. It didn't run anything. So it just says this is some comment to yourself. And if there are no errors that occurred, we should have this blue caret pointing and then a blinking cursor. Right? So we are good. Now that was the first step in what I call downloading the packages or creating local copies. So a good practice to get started with is making comments. Right? So we already commented out install.packages, but that's not necessarily a comment to ourselves, like a note to remind us what was going on. So I'll make a comment here that says download and install local copies of packages. That way, this is telling me everything below this line is installing these packages, right? But that was the first step. We made the local copies. We're not actually using those local copies yet, right? So we have to tell R, actually use those or load these packages, use these downloaded packages. And to do that, we say we're going to load them as libraries. So the line of code to load those packages that we just downloaded, mass, psych, and hmisc, is library with each of those packages listed. So we'll see blue library, and inside the parentheses, we'll see the name mass, we'll see the name psych, we'll see the name hmisc. You'll note here, when we're calling the library, we don't need quotation marks. So that's the difference there. So when we want to load these packages, we just highlight all of those and then run them. Command Enter, Control Enter. Okay. So what just happened? A bunch of red text. Did you mess up? No. It said loading required packages that are related to all of these packages and attaching package hmisc. All of these packages are attached. I don't see any errors, so we can assume that these packages are loaded. A good way of checking if these packages were actually loaded is to actually go over to this window. your viewer window, click on Packages. And earlier I mentioned, you know if a package is loaded if there's a check mark next to it. So we said we wanted mass, psych, and hmisc. So let's scroll down. A lot of these aren't loaded, but let's see. hmisc, there's a check mark there. That means we brought it in, and now it's loaded. Mass, where's mass? Mass is loaded, right? It's downloaded because it's listed here. It's loaded as a library because there's a check mark. And then finally, psych. Where's the psych package? Psych, same thing. All right, so all of those are loaded. I'll make another comment here that says load those packages. The next step, it's important to remember that once you've installed a package, you never have to reinstall the package unless you re-download R, right? So because I don't intend on re-downloading R, I can go ahead and either delete these lines of code or just comment them out, because now nothing needs to happen there. Right? Oftentimes when you open up an R script, you won't see any of these. So we can just delete that. But you will see lines of code that have library, just a long list of different libraries that are being loaded, or packages that are being loaded. Awesome. So, like I said before, in many of these packages that are housed on in repositories or in the cloud, they come with datasets, and these datasets are free for everyone using R to use. So if you want to use one of these datasets, let me clear this bottom window with Control L. If you want to use some of these datasets, you have to figure out what are the datasets' names. I won't go through the practice of finding out what the datasets' names are, but I will say that the mass package, accordingly here, comes with a data set on car manufacturers, or motor trend cars, MT cars. So the data set is called MT cars. So if I wanted to call that data set, I could go here in our console window and write MT cars. And that data set comes up, right? It's about 32 different cars, right? Different kinds of cars, and then various components or features of those cars, also known as variables, right? So we have observations. Each observation is on a row. It represents one car. Each variable or feature is on the column. So MPG, miles per gallon, the number of cylinders, we have horsepower, we have the weight of the car, right? So all of this information. But I just called it down here, right? Remember, I could write it up here. I'll give myself a comment, call in the MT cars dataset. So I'll write MT cars. You see that it popped up when I started writing, right? MT cars. I'll clear this window again. So now I can run this whole thing, and that pops up again, right? So the difference is, if I just type it down here, it's not going to save it. You saw how I cleared my window. It's not going to save it. But if I want to save the script that I'm doing, I'll write it up here. The interesting thing about these data here is that we can't really do anything with them. And that's because it represents sort of an image of the data set. It's like somebody showing you a PDF of, or giving you a piece of paper with data on it instead of just handing you the data, making it usable in an electronic format. So this is sort of an image of the data set, and we want to use that data, or those data. So instead of just calling MT cars, we have to pull it into our own working memory. We can't just say, hey, what is that data set in the cloud? What does it say? Instead, we want to actually pull it into our own environment and make it a data set of our own. So to do that, in R, we have something called the assignment operator. So I've previously mentioned that R is an open object-oriented programming language, right? Not only is it open source, but it's object-oriented, meaning you can pull in things and name them new objects, create objects out of other objects, right? And to do that, we have to use what's called the assignment operator. And the assignment operator basically says we're going to take the old dataset name, dataset, point directly at the new name we want to give it. We're creating a new object out of it. So we're saying, take this old dataset data, take these data and put them in this new object that I'm going to call it. Right? So here I've given an example. Data1 equals, and we point to data1, we call it empty cars. So here, instead of just calling empty cars, I could say data empty cars. You'll notice in this example, I don't include spaces. That's just to save space. However, convention, good, best practices in writing code, whether it's R or Python, is to include these spaces. So I can call this data instead of just calling the empty cars dataset. So let me clear this bottom window again. I'm going to run this line of code. And when we run it, nothing should show up here, but because we're creating a new object called data out of the old object, empty cars, we should get a new data set in our environment, meaning this new data set should go over here into our environment. So let's run that. Okay, we didn't see the data pop up down there, but now we see the data up here. 32 observations, 11 variables. If we want to see if that actually matches up with our empty cars data set that looks like this, we could just click on the word data and it'll open up essentially a spreadsheet of the data set, right? Mazda RX-4 is the first one. Mazda RX-4, 21 miles per gallon, 21, 6, 6, 160, 160, right? So it looks like it matches up. So we have each car is a row, is an observation, 32 of them, and then each column is a variable, 11 of them, right? So we have that. If I wanted to pull one of the variables out of there, let's see, we have cylinder, we have weight, which is WT, we have number of gears. Let's say we wanted to pull out the variable weight. So I'm going to tell R, just pull out the variable weight. I want to see the values for weight. We'd say, we have to tell R, well, where is this variable weight coming from? Which data set and what variable are you looking at? So we said we want the variable weight. And if we remember, the variable weight is WT. So we say WT. Right? We can call WT. What happens? Nothing. R says, what the heck is WT? I don't know what you're looking for. For R to know what it's looking for, you have to tell it the data set or the object that you're pulling this weight variable from. Right? And to do that, in R, we use the $sign operator. So it says, what is the name of the data set called data? Then we say $sign separates that and the variable name. So data $sign weight. So instead of just weight, it's going to be data $sign weight. Now we run that. It should work. So we're going to say call the weight variable from the data set. Right? So it says 2.620, 2.875. So let's go to weight, 2.260, 2.8675, 2.320, right? All of those are matching up. So this essentially just lists everything in that column. We can do the same thing for MPG. How would that go? Well, we need to first tell it what's the data set name, $sign, what's the variable name. So which variable was coming from which data set. So the data set is called data. We say $sign, and look, when we type that in, it gives us all the list of the variables. So we'll say MPG, let's list that. 21, 21, 21, 21, 22, 22.8, 21.4, 21.4. So it's matching up, right? If we did that here, we could say call the weight the MPG variable from the data set. How do we do that? We say data, $, and look, MPG pops up just like it did down there in the console. Here it would be deleted, right? Because I can Control L and it's gone. But here it's saved. Well, we can save it. Okay. We'll run that. I'll list everything we just saw. Awesome. So now we know how to call variables from data sets. What happens if we didn't have that name data? We had the name cars. Well, we would say we're going to call this new data set. Instead of calling it data, we're going to call it cars. So we'll run that. And now we have a data set called cars. Right? But you'll notice it's the same data set, right? Because it's pulling from the same empty cars object. Cars and data are the same data set. They're just named differently. Right? So we're going to look at that. Looks the same as the data set, right? No changes. So if we wanted to call cars, pull from cars, we could say cars, $, and weight. We'll run that. Cars, $, MPG. We could run that. Right? That looks a lot like data, $MPG. Right? So just think about this. Keep this in mind when you're naming your data sets, that you're going to need to call variables from within that data set this way. Awesome. So next, we are going to focus on actually running some univariate statistics, right? So we have the stock summary function that comes in R. We can get the mean, median, third quartile, first quartile, max and minimum for all the variables in the data set, right? So we can just run summary on our data set called data. We can also use that summary function for each variable. So here we just called, before we just called the data set. That means it's going to take a summary function of all the variables. If you highlight or specify the MPG variable or one variable, then you can get all of those characteristics for just that variable. In the psych package, we also have the describe function. So that'll give us information about all of these variables. So here's the MPG variable, here's the cylinder variable, disp, HP, all of this stuff. Instead of doing that, I feel like it's wise to practice running these univariate statistics one at a time. Right? So if we wanted to calculate the mean of MPG, right? So let's clear this. Calculate the mean of MPG. Let's call that again, data MPG. We would have to say, we would sum all the values up, then divide by the total number of observations, which is 32. So sum all 21 plus 21 plus 28, 22.8, 21.4, all that through 21.4 divided by 32. That would give us an average, or the mean. However, luckily, in R we have stock functions on the mean of MPG. To do that, we'd say mean, which is the function, and then you tell it which data set we're using. So we're using the data set and on the MPG variable. We run that, hit enter. The mean of MPG in the data set is 20.09. Right? We wanted to run on a different variable. We say of cylinder. Run that. There we go. Right. I'm just going to put this back on MPG. Cool. Now it saved us a lot of headache. We don't have to calculate by hand 21 plus 21 plus 22.8 all the way through the end, divide by 32, and get that. We just have a simple function. If we wanted to run the standard deviation, the function is called, so run the SD of MPG. We'd say SD data MPG. We run that. The standard deviation for the MPG variable is 6.026948. Right? Nice. That's really easy. We can do the same thing for almost all other univariate statistics. right? We can do, let's see, median data MPG. Okay, so this is going to be, just highlight that, copy it, run the median of MPG, run that. 19.2 is the median. So instead of organizing these numbers from lowest to highest and then crossing off the end and finding the minimalist point, we've done that through this function. If I want to run the minimum, we'd say min of data MPG, which is 10.4. So that means the lowest value here should be 10.4. How do we check that? We can actually go into our data set, go to MPG and sort from lowest 10.4 to highest 33.9. So we know that the minimum is 10.4. That also means that the maximum, the highest value, is 33.9. So let's try max. Let's run the max. And the maximum of MPG, max, 33.9. Awesome. Now we have that. We can calculate range in various ways. We can use range function in R, but usually that just tells us the lowest value and the highest value. You can calculate the range by doing it minimum minus the maximum. All right, so you can do it various ways. And next, let's clear this. I want to show us. So now we have all of those univariate statistics. To run the mode, it's a couple of extra steps, but it's not necessary to find just yet. So next, we're going to focus on creating a histogram, right? And a histogram works for interval ratio variables. It's a bar chart that works for interval ratio variables, continuous variables, right, where the bars are touching one another. Luckily, in our data set, all of our variables are interval ratio, right? They're numeric, right? We can highlight over there, numeric, 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 right? So these are all numeric values. So we can use a histogram. So we can go back to this example here and see that we can run a histogram through this function called hist. And in the hist function, we call the data set that we're interested in, $, and the variable, right? So we're calling the MPG variable from the data set. We're going to create a histogram for it. So, all right, create histogram for MPG variable in data set. So to do that, we say hist data, which is the data set we're interested in, $, and then look MPG, right? So what should happen is, because this is a plot, it should pop up in our plot window, which is this bottom right. So let's go ahead and run it, hit enter, and there we go. We have histogram representing miles per gallon on the x-axis, the horizontal axis, and on the vertical or y-axis we see the frequency, so how many cars had this amount of MPG. And they're bend pretty wide, right? So it's 30 to 35 is one bend, 25 to 30 is one bend, right? So we can make those different, we can change those up. No need to go into that detail just yet, but just know that you can separate these bends. We could do one bend from 10 to 35, right? And that would include all the cars, right? So these bends are very important. All right, that's how we run a histogram. And then finally, I wanted to show you how to create randomly generated, normally distributed data. So in R, there's a function called norm, or rnorm, which represents randomly generated, normally distributed data. Right? And that R function takes 3 arguments. The first argument is the number of cases that you want to include. The second argument being the mean that you want this to represent. And the third and final argument representing the standard deviation that you want to have, right? So here I have an example. Our norm is 100, 0, and 1. So our norm with 100 cases, with a mean of 0, and a standard deviation of 1, right? This is also the stock version, so you can just run it with rnorm 100, and it's going to give it a mean of 0 and a standard deviation of 1. But you can run this for however many cases you wanted, whatever mean you wanted, whatever standard deviation you wanted. Right? So I'll take this, say, create randomly generated. Right. So in this, we should, when we run the rnorm function, it should just give us the data set that we want, 100 cases with a mean of 0 and a standard deviation of 1. Let's run that. And look, now we have 100 cases. We have first case, 7th case, 13th case. This one's the 97th, 98, 99, 100. So that's 100 cases. If we wanted to do 5 cases, we could do that. It's going to give us 5 cases. If we want to go back and do 100, let's do it again. 100. Okay, the first case on this 100, let's clear that again. Let's run this twice. 100 cases, and then we'll run it again, 100 cases. So the first case on this second run is a negative 0.01. The first case up here is negative 5.7. Wait, we just generated these data sets. So why are we getting different numbers? Well, that's because it's randomly generated, normally distributed data. So what we're trying to do with this data set is create a normal distribution. We know what a normal distribution looks like. Here we have data for MPG. It doesn't really look like a normal distribution, right? Sort of, but not quite, right? It looks more skewed. So we're trying to create a normal distribution, but how can we tell? Right? These all should follow a normal distribution. They should have a mean of 0 and a standard deviation of 1. How can we tell? Remember, when we run it like this and it just populates in this console window, it's essentially just giving us an image. But because it's randomly generated, you're going to get different numbers every time. Negative 0.54 is the first one. 0.11 is the first one. Negative 1.685, right? So it's going to randomly generate numbers that situate around 0 mean, standard deviation 1. To actually save this as a data set that we can use instead of just an image, that way we can check the means, check the standard deviation, and also run a histogram to see if it's normally distributed, we need to save it as an object, meaning we have to put it in this environment. How do we do that? Remember, that's the assignment operator. So we use the assignment operator and say new, so norm data is what I'll call it. I'll just call it norm. I'll run that. And now down here, all it says is the line of code. But up here, now we have a list of values, rnorm, right? So that's just, it's going to range 100 cases. If we said rnorm was 5, we look up here, because we give it the same name, norm, but now we've changed it to 5 cases instead of 100, it's going to replace that norm value there. Instead of 1 to 100 cases, it should say 1 to 5 cases. So let's see. And that's exactly what happened. It went from 1 case to 5 cases, right? We said 5,000, it'll do the same thing. Now it's 5,000 cases, right? But the difference between a data set and values is that data sets have multiple variables. Values just list the value for one variable. So before, when we had to run a histogram for MPG, we'd have to say histogram, go into the data set called data, and find the variable named MPG. Here, we're not going into a data set called norm, right? We're just finding the variable called norm, right? It's a variable by itself. So if we wanted to check the mean and standard deviation, how do we do that? For this norm variable that's by itself. Well, we say the mean, right, of norm. Remember, we called a mean of 0, standard deviation of 1, so the mean should be pretty close to 0. And what do we see? It's pretty close to 0, right? Negative 0.008, right? So that's pretty close to 0. If we had to round, that'd be a 0. Let's check the standard deviation of norm, that variable norm. Should be pretty close to 1. And we see it's 1.01. Okay. We can do the same thing here. Remember, we started with 100 cases. So if we reran this, it's going to change this from 1 to 5,000 to 1 to 100. Okay, there we go. Let's get the mean for that norm. 0.04. Right? So that's close to 0, but not as close as it was before. This SD for the new norm of 100 cases should be close to 1, 1.017. Okay, still about the same. Right? Let's say we wanted to run a histogram just to see if it does look normally distributed. We'd say hist, and then obviously norm. So now let's run histogram for norm. And we look at that, and that looks pretty close to a normal distribution. Right? But as we notice, the data sets change with the size of the cases. Right? So the means change. Not only do the data sets change every time we run this, but with the size of the cases, the means change, the standard deviations change, as well as the form of the histogram. Let's say we only wanted 10 cases. Let's rerun all of these. So I'm going to clear down here. So we want a mean of 0, standard deviation of 1. So let's rerun those. So mean is negative 0.1. So that's not as close to 0 as it was before, but it's about 0. And then 1.1. Now let's run a histogram for that. Oh, wow. That doesn't look that close to a normal curve. Right? It's missing a block over here. Right? Let's try it again. Let's rerun that same thing. So every time we run our norm, it's going to give us a new norm data set. So here we have negative 0.63, 0.684, 2.2. Let's rerun it again. Now we have a bunch of different negative numbers, right? We also know that the means changed from negative 0.1 to 0.19. The standard deviation changed from 1.12 to 1.24. Also, the histogram changed. It doesn't look close to a normal curve at all anymore. So let's do it again. So we can run this over and over again and see if we get close to a normal curve, right? That's sort of there, right? None of these are actually normal curves. But as we mentioned before, with increasing number of cases, right, we reach this sort of this idea of the central limit theorem, but we also get closer and closer to this, the normally distributed bell curve. Right? So here we had 10 cases. Let's increase it to 100. Let's rerun all of these lines. That looks closer to a normal curve. Let's run it again. Again, kind of like a normal curve. Again, kind of like a normal curve. Let's try with 1,000 cases. Let's run that. Wow, normal curve, normal curve, normal curve, right? These are all looking more and more like a normal curve than it did with 10 cases. What about 10,000? Right? Now it's not changing much, the actual shape. It's changing the range of the values, but the actual shape doesn't change much. Let's try 100,000. Right? The actual shape isn't changing much. Right? So with increasing numbers of cases, the more and more it starts to look like an actual bell curve. Right? Do not do much more than 100,000 or a million. I think I accidentally did a trillion before, and my computer, I had to shut it to stop it from running. So keep that in mind while you're playing around with this normalizing function. All right, that's all I have for you today, and hopefully that made some of the things a little bit more clear for you when it comes to R and univariate statistics, normal distributions, and histograms altogether. Right?